Good morning, everybody. I hope you can understand me well. I have a little bit of a cold, but I'll do my best for the next 20 minutes. I hope it works out. My name is Jacob Eberhardt. I work at the Technical University in Germany as a researcher, and I'm here today to talk about Socrates, which is a toolbox for zkSNARKs on Ethereum. It was first introduced at DEF CON last year, and now we made some progress in development, and we like to update you. So some of you may have heard of the project, others probably haven't. So my plan is to first give you a quick motivation for why this thing exists, then give you an overview of the tooling and what it does. Then I would like to talk about applications a little bit, and in the end, talk about our roadmap and what we're looking to do in the future. So let's jump right into it. Here on the left side of the slide, you see how transaction processing in blockchain usually works today. So you have a transaction, you send that transaction to the network, and then every node in the network processes it, and that means re-executing it to make sure that it's actually a valid transaction. So that's what we have now. Now imagine if we had this on the right side of the slide, where a transaction is sent to the network, but instead of being processed on every single node itself, it is delegated to a third node, to an outside party, and there it is executed, a computation is performed, and then the result and the proof regarding attesting the correctness of the execution is written back to the blockchain, and then only that proof is verified on the blockchain. So the main part of the execution happens off-chain, actually. Okay, can we do this? And what does it bring to the table? Let's look at that now. So what are the benefits of off-chain processing if we can do it? So scalability would be one thing. If we can verify computations on-chain cheaper than re-executing them, then we can fit more processing in one block, essentially, on the blockchain. So that also means the block complexity limit does not apply in the sense as it applies at the moment. There's also confidentiality or privacy, as some people call it. That means private information can be used without revealing it in that case, if we have proofs that do not reveal anything about the data we work on off-chain. What are approaches to implement this kind of idea? There's basically two. One is TrueBit, which is more of a computation marketplace, and it works based on crypto economics. So computations are delegated to an off-chain party and executed there, and then results are written back to the blockchain. But instead of having a proof regarding the correctness of execution, what they do is they provide incentives for others to prove that the people who posted the results were wrong. And we do it another way. Here we use zkSNARKs. We could use other mechanisms, but at the moment they're not quite efficient enough for use in practice. That would be zkSNARKs and bulletproofs, which do not require a trusted setup, which is a charming property, but they're not as evolved yet, so there's still research going on there. So we use zkSNARKs, and let me briefly talk about what zkSNARKs are, so that we're all on the same basis. So zkSNARK stands for Zero Knowledge, Succinct, Non-Interactive Arguments of Knowledge, and that's a type of computational proof that is short and non-interactive. Non-interactivity here means that I can simply take a proof, send it to someone who's supposed to verify it. He can then do it without any further message exchanges. So it's a one-round protocol. There's zero knowledge. That means they don't expose any information that went into the generation of the proof. And another cool property we use here is that the verification cost is not dependent on the complexity of the off-chain computation. So you can have a very, very complex off-chain computation and still verify it with the constant cost of on-chain. That also means, though, that very simple processing steps would cost more to verify on the blockchain with this mechanism than executing them on-chain in the first place. So in that case, we don't gain anything. It's use case dependent. What you actually prove from an abstraction standpoint is that you know a satisfying variable assignment for either an arithmetic circuits or rank 1 constraint system. And as you see, they look a bit complex and not good to deal with. And that's essentially where Socrates comes in to provide a better abstraction to specify computations that can then be off-chain and integrate them. So how does the zkSNARK process work briefly? On the left side, we have a circuit or rank 1 constraint system that encodes the computation. In that case, we have an example where we multiply by two numbers and say it equals the third number. Very simple. First, we need to do a setup, and that's the pain point, which is not solved yet, but there's ways to deal with it. So we do a trusted setup once. We have to trust the participant who does it or move to multi-party computation protocol if we do not want to trust a single entity. And that generates a proving key and a verification key. Using the proving key, I can then find the solution to the system and use the proving key to generate a proof that I correctly executed this computation and publish the result. I send these two things to the verifier, and the verifier can then check whether I found the solution to the problem, but the verifier cannot learn anything about the private inputs that I use. In that case, the verifier cannot learn anything about X and Y. He only knows Z, and that I know a factorization of Z. That's all he learns. Okay. With the Byzantium release, Ethereum added support for zkSNARK verification. That means 3 precompiles were added, and that's elliptic curve multiplication, addition, and the pairing check, which is a kind of homomorphic cryptographic operation used in a proof verification. But the big question remained for most people, how do I use that? That wasn't clear. That's where Socrates comes in. So the tool has the vision to provide usable abstraction and tooling for zkSNARK so that it can be used on the blockchain more conveniently than specifying rank 1 constraint systems, understanding proof systems in depth, and writing your own verification contracts in Ethereum or whatever, because that's quite tough to do. It's supposed to support the complete process. That means program code is specified, and then it goes all the way until the proof regarding that program code can be verified on the blockchain. It's built to seamlessly integrate with the Ethereum blockchain, and another goal is for it to act as an integration platform, because there's new proof systems evolving, coming up, and they work on the same abstractions, so we could ideally integrate them also in here so that we can use other proof systems as a backend and maybe move away from the trusted setup. Also, there's new ways to specify circuits. I've seen new approaches based on functional programming, and it would be cool if we could just reuse circuits or programs that have been built and not work in silos. So that's why it also has the vision of being an integration platform. So it comprises a high-level domain-specific language to specify computations in a way that's more familiar to regular developers than working with arithmetic circuits. A compiler which transforms these programs into provable constraint systems, and then further other tools that help along that way. We'll see that in a minute. Okay. The language is actually a quite simple imperative language. The basic type we have is prime field elements, and you can think of that as positive numbers that can be very large but always stay below a very huge prime number. So just think of it as positive numbers for now. Then there's imperative statements, assertions, loops, so the things you know from imperative programming languages, also conditionals and functions. Okay? And that's I want to spend a little bit of time on that slide because that covers the overall process, how the tool is used from a user perspective and what you can do with it. So we start with high-level code. In the language I just told you, we specify a program we want to prove, and then we compile it. And then we have so-called flattened code, which is essentially not quite equivalent, but close to a rank 1 constraint system, which I can then use to do proofs on. This flattened code goes into the setup phase and generates a proving key and a verification key. based on that verification key, I can directly export a Solidity smart contract, which I can then deploy to the blockchain to check proofs, okay? So that's what the tool already gives you, a smart contract you can use for on-chain validation. The flattened code also can be used to generate a witness, and that essentially means finding a solution for the program you specified. In the example we had, that means for our system x times y equals z, we just find 3 numbers that fit the system. Based on the witness and the proving key, we can then actually generate a proof, and that proof will be then delivered to the blockchain for verification together with the result of the computation. So in our example, x times y equals c, that would mean we have a value for c plus a proof, and that's sent to the blockchain and can be verified with the verification smart contract, which is, which you see at the very bottom of the slide here. Okay, the on-chain proof verification process. So the proof itself, it's rather small. That's the succinctness properties of zkSNARKs. It consists of currently, with the proof system we're using at the moment, 8 elliptic curve points. So that's not a lot. It's actually quite brief. And besides that, there's the result, the set in our case, and potentially inputs we also want to expose to the public. That could be, for example, we also want to expose the X in our computation. Then it would also be part of what is sent to the smart contract. And that contract has the verification key included at 7 elliptic curve points, and it has a verify function that can verify proofs and also check whether the result is correct for the given program, using the precompiles that were introduced with Byzantium. At the moment, with the proof system we're using, that costs 1.6 million gas. So that's quite expensive, and that's where I said it does not make sense to put very cheap off-chain computations in that system. There are new proof systems that get better there, and then of course the break-even point moves further down in terms of gas cost. Okay, let's look at what we can do with it. What can it be used for? So on Reddit, about 2 weeks ago, there was a post, and there was a guy who wanted to give $10,000 to the person who could guess a correct permutation of a card deck with 52 cards. That was on Reddit. So what are the challenges involved here, and why is it related to Socrates in any way? So first, that guy needs to pay the $10,000 to the contract and commit to a permutation of the card deck by publishing a hash. That's how you usually commit to values. And then as soon as they're published, the hash can be checked on-chain and you're paid out, right? But there's another challenge in this scenario, and that's that you have to prove that you committed to a valid permutation without revealing the permutation, because otherwise he could have just committed some hash that is not a hash of a valid permutation, and that would never be a solution. So he essentially wants to show that there is a solution. And this third part here is where Socrates comes in, because that's what you can do with the tool actually. So you check card validity, you check card uniqueness, and you hash the permutation, and you return the resulting hash. That's what you specify in a Socrates program, and then people could check that there is actually a valid solution for the problem, but they learn nothing but that there is a valid solution to the program, and that's checked on-chain in a proof. Okay? So what we found out, looking at different use cases that are interesting, oftentimes different cryptographic primitives are needed, and that's a bit of a problem because we don't want to reinvent the wheel and implement all types of hash functions and encryption functions and stuff in the domain-specific language, because that's painful to do. It takes a lot of work, and there are already implementations of that kind of stuff. So what we focused on now is helping with integration of these primitives, so we get hash functions, encryption functions, all that kind of stuff to the platform, and can potentially have community contributors help out there, so we can focus on the main platform, maybe move to other proof systems, but still enable use cases. For that, we implemented multi-returns, rank 1 constraint system importer, and better semantic checks and integration tests, so you can make sure the things actually work more conveniently. Now I want to talk about a couple of other applications or things you could do with it that come to mind. So what we talked about a minute ago was where I was proving the knowledge of a secret. What I can also do with a tool like that is prove, for example, that I'm a member of the group without showing which member of the group I am. It's also something I can do. So generally, facts and private data without publishing the private data is one use case. What's also quite interesting for some applications is that I can do very brief Merkle tree membership proofs. Instead of using traditional Merkle proofs, where I basically, if I want to prove that D is part of the tree with this root hash, I have to supply this and have to supply this. And the larger the tree becomes, the larger the proof, that Merkle proof also becomes. So what we can do now, because the certain other proofs have fixed size, we can just show that that D hashes with other private values, which I don't even have to make publicly known, to this root hash. And that's just also a regular zero knowledge proof, and that becomes very brief, and that can be very interesting for on-chain applications where hashing along a very long Merkle path is extremely expensive to do in smart contracts. You can implement shielded tokens like zcash. As far as I know, there's a couple of people working on that on top of Ethereum now. And also a cool thing you can do, it's a bit more abstract, is you use the blockchain for what it's very good at, and that's on-chain state. So state is what the blockchain is very good at, because you know the data availability problem with all data that's off-chain, and you don't have that on-chain by definition, so that's why probably a lot of state needs to be kept on the chain. But state transitions, all we need to know about state transitions is that they happen correctly. There are no mistakes being made, and they're valid. So what if we kept the state on-chain, but made the state transition functions off-chain and only showed that the state transitions that occurred were valid according to protocol? Then that would also offload quite some work from the blockchain, and that could also be a cool application here. For Socrates, a bit of a roadmap, and where people could contribute. Also, we're actively looking for a bit of help here, because it's basically a research prototype, and we have some people who started contributing. So if you're interested, please feel free to talk to us and see where you can maybe help or fit in. So big topics are integration at the moment. That means using all the or bringing together all the silos that have built up that all generate maybe rank 1 constraint system from different abstractions. We're currently trying to agree on a rank 1 constraint system standard with a couple of people from zcash, from Quedit, and other guys. I hope this works out. We have a draft version, so that's good. That can be imported also. We look at other proof systems. I think the next step would be to move to the Croth 16 snark, which makes the proofs much cheaper to verify, because there's the pairing checks reduced, and the proof size also comes down, but it gives essentially the same guarantees. We look at integration of a prototype of a distributed setup phase, like zcash performed off-chain, but with support of an on-chain coordinator as a smart contract, essentially. Also, we look at new proof systems. They're a bit tough to use at the moment, because the proofs are still quite big, and with that not optimal to verify on-chain. But the cool thing about these new systems like bulletproofs is they do not require trusted setup, which would be a big step forward, I would say. And regarding the Socrates language, there's also work to be done. Type extensions comes to mind here. With that, I would like to conclude my talk. Thank you very much for your attention, and please feel free to try out the tool, create issues in case there's any bugs, or generally reach out if you're trying to contribute or want to use the toolkit. Thank you.
So yeah, I was just wondering about that setup phase, and whether that's something that's dealt with like by the individual user, or is that like compiled into Socrates somehow, and if so, how, in what way is it?
Okay, so about this setup here, it's it's in Socrates, so the setup operation, that's command line operations you see written down in blue here, allows you to perform a trusted setup locally on your node. So that might be fine for some users and some use cases, but might not be fine in many other cases where you do not trust the person that you interact with via the verification smart contract in the end. So for that case, that's what I was talking about in the Outlook. We're looking at distributed protocols to better work with setup protocols that need only one participant out of a whole group, to be honest, to then be completely safe. There is a cool new protocol by the zcash guys. They're currently in the first phase of that protocol, Powers of Tau. But the problem with that is that they use a new elliptic curve, and Ethereum does not have the precompiles that are required to work on or to validate proofs on that elliptic curve. So we currently cannot use this setup phase done by zcash for the proofs on Ethereum. So that might happen in the future. I don't know what the foundation standpoint on that is. I don't know. Yes.
So you mentioned one of the potential uses was being able to turn things like Merkle proofs from O-log-n into O1, basically. Where would you estimate the trade-off point is, or the break-even point is there? How big does your set have to be for it to be more efficient to do it this way?
So I have not tested it, but I talked to Justin Drake recently, who kind of had the idea in context of stateless clients. And what we tested is that generating the proof took 5 seconds for a Merkle tree of depth 64. And I think in that case, it's already a much shorter proof than having the many hashes. So in that case, it would already, the break-off would already have happened.
So a Merkle tree of depth 64 could enumerate every sand grain on Earth, which is a bit of a large cap. Do you know like roughly what you're talking in terms of gas for verifying something like this?
So the zkSNARK verification is always equally expensive, 1.6 million gas. I don't know how expensive it is to verify it on-chain at the moment, just using hashes and going along the Merkle path. I have not tested it.
Cool, thank you.
Hello, I have a question which is probably related to the trusted setup, but assuming that there's a trusted setup that happened, how do you certify the circuit itself? Because once you just commit to the Ethereum blockchain, the verifier smart contract, it's just going to call a verify method that's in fact just an arithmetic circuit. How do you trust that it does verify what you want? Because if anyone can set up a prover kit, how do you know that there's not even a bug in the compiler and the verifier doesn't have loopholes? How do you certify that?
I'm not 100% sure I actually got the question, but let me try to answer anyway. So the setup phase happens specifically for one program. And both of the outputs, the verification key and the proving key, they become public. And
yeah, but the circuit itself is quite hard to audit because not anyone can just look at the arithmetic circuit and says, yeah, it does verify an elliptic curve add. So okay, how do you convince people that the circuit really does add points on the elliptic curves and that the verification is correct without just first testing all inputs?
Okay, maybe there's 2 aspects. So the verification key and the proving key, they belong together very specifically. And you can never create, unless the setup phase was compromised, which we assume it wasn't, you can never create a proof regarding the execution of another program that would be verified by a verifier for a different program. So a part of the check that happens in the verification smart contract is to make sure that actually the same arithmetic circuit was used. So that is explicitly checked as part of the verification. So I think what you sketched out, that cannot happen.
Yeah, but still, still, even if you're using the right arithmetic circuit, how do you know that this circuit does the job you want it to do? You have to trust the higher level Socrates language, and both trust that the compiler correctly compiles it to a circuit.
Are you essentially asking whether I should trust the trusted setup? Because I have to trust it. That's
not really the setup, but the execution and verification. Because it's not normal code that computer scientists understand by just looking at the code. It's an arithmetic circuit. So how do you know that an arithmetic circuit that is supposed to check that a balance value is in a range really does check that? Apart from sending random inputs and convincing yourself with enough input, but.
So I'm not sure what you could maybe do is you distribute Socrates.code files, everyone compiles them for themselves, and because it's deterministic, you can check hashes on that and compare that maybe. But I think that's a very general problem in computation and not specific to this system.
But if, for example, you have a circuit that verifies that the balance is, that the number is not more than 100 and 1,000, and if in fact you just in the circuit, the circuit just verified that it's not more than 90,000. Most people will think it works because on the input they tested it works, but in fact it doesn't. There's a kind of backdoor in there, and how do you know that? That's the same
with every program, right? If the compiler does not work correctly, if the compiler has bugs, then what you execute is not what you specified. So in that case, of course, you trust the compiler as you trust every compiler, and we need to make sure it works as intended. So all you could do to make sure is maybe then test it or something, or for now trust that it's correct.
Okay, thanks.
Okay, we're out of time. So, thank you very much.